I'm Antonio Sala, and in this video we will work through a Matlab example of working with a symbolic toolbox and manipulate partial derivatives, Jacobian matrices, and computing that kind of physics jargon that is called total derivatives. We will define a couple of ordinary Matlab functions, f and g, so f takes 2 inputs and gets 3 outputs, and g takes 2 inputs and gets 2 outputs. Inputs must be in vector form, so f is evaluated like this and g is evaluated like this. However, with numeric functions, ordinary code, we cannot take derivatives. Well, I mean, we can in some ways, some of them approximate, but come on, the symbolic toolbox is built for that, so we will replace the numeric arguments of f and g by symbolic toolbox objects x1, x2, y1, y2. So we have this symbolic f and symbolic g. So now let's go to the main objective of this video, which is illustrating how to do partial derivatives, chain rule, and that sort of stuff. Diff computes the derivative of one symbolic expression with respect to a given variable. Here we have it. So this third element of fsim, this thing, when we take the derivative with respect to x2, we get this stuff. And I really thank Symbolic Toolbox avoiding me the tedious way of computing this kind of things. Okay, so we have this derivative. If the first argument to diff is a vector of expression, then it takes the derivative of each of them. So if we differentiate, for instance, all of fsim with respect to x1, then we get like x2 minus 2x1 and 0, because the last one does not depend on x1. So this is what the diff commands output. As fsim here depends on 2 letters, x1, x2, if we arrange the partial derivatives with respect to x1 in the first column and the partial derivatives with respect to x2 in the second column, then that's called the Jacobian matrix. The Matlab command Jacobian does exactly that. It takes all the letters in fsim and each of them goes to one column. Well, in lexicographic order, and capital letters first, just like in a dictionary. More on that later. So, well, in this Jacobian matrix, if I have 3 outputs and 2 inputs, then rows refer to outputs and columns refer to inputs in this arrangement. So, for instance, this will be the partial derivative of the third element of f with respect to the second input, third row, second column, and likewise with the rest of elements. As g has 2 inputs and 2 outputs, then okay, its Jacobian is this 2 by 2 matrix. As the order of the columns and the arguments of a function is actually arbitrary, well, if we wish a particular order in the columns of partial derivatives, we can enter a second argument to Jacobian, telling them which partial derivatives go to the first column, in this case, the derivative with respect to y2, and which one goes to the second column. So in this case, you can see columns are swapped with respect to the default ordering. And also, the second argument is helpful in many cases because, for instance, in equations in physics, we have a lot of letters that are actually constants, say a mass, a length. So we actually don't want to take derivatives with respect to the mass, because that mass is just 3.1, like a number. So when we have that kind of letters, we do not want to take derivatives with respect to them. Then okay, we can just call Jacobian, omitting that letters from the second argument. So using the second argument in Jacobian makes things more readable. Let's now illustrate how chain rule works by considering a new function z of y, which is the composition of f and g. I mean, instead of doing f of x, now we replace x by g of y. So this is z. 2 inputs, 3 outputs. Of course I can compute it. It's Jacobian, and it's this kind of stuff, in which, well, the third output is a kind of long stuff, but okay, that's what computers are for, no problem. Just swallow that. So how can we obtain exactly the same result with the chain rule if we know the derivatives, the Jacobians, of the constituent functions f and g? Well, chain rule tells us that the product of the Jacobians will give us the Jacobian of z. The product of the Jacobians of f, which is this stuff, and the Jacobian of g, which is this stuff, is this matrix. However, we see that there is a problem. I mean, chain rule temporary has 4 letters in it. It depends on y1, y2, as expected, but on x1 and x2. That should not happen. Indeed, to finish the chain rule computations, come on, the inputs of f are actually the outputs of g. So, with command subs, I substitute, and when I see x1, I actually replace it by the first output of g, and when I see x2, I replace it by the second output of g. Then we have applied chain rule correctly, and this chain rule final form, all this stuff, okay, with this sigma 1 actually amounts to this horrible expression. Well, this chain rule final form is actually the Jacobian of the function computed without considering that it was f and g, just substituting before taking derivatives. Indeed, Symbolic Toolbox tests that the two results are identical, as expected. In summary, this Matlab code has checked that substitution first and partial derivatives later, so the direct way, we did first the Jacobian of z, gets the same result as chain rule, derivatives first, product of Jacobians second, and substitution last. Good. We'll now see a second example of chain rule using the physics jargon of partial versus total derivatives. What's that? Well, it's just chain rule. Don't be afraid. I mean, in physics, there is a special letter, a special variable in dynamics called time. The objective of dynamics is assessing properties of the evolution of things with respect to time. So everything will be a function of time. Let us imagine that, for instance, the two inputs of function g are actually functions of time. I can have like two angles in my wrist, and then g will give me the horizontal and vertical coordinates of the tip of my finger. Then we wish to obtain the speeds of the tip of my finger from the speeds of my rotations, say, of my angles. This is the kind of problems these discussions usually apply to. So I will know that y of t, the two inputs, are minus t and t squared, and of course later on its time derivative. It depends on only one argument, so it's diff, no need of Jacobian. Okay, it's minus 1 and 2 times t. So imagine that we have a function of both these y things and the time itself. For instance, say that q is function of the angles, let's say, of my wrist and fingers, that would be y, and some fixed movement of my wrist up and down, that will be this, what we call explicit time dependence, while in this case, until we plug that y1 and y2 are actually functions of time, this is a dependence that it's not clearly seen here. It's what we call an implicit dependence, because, okay, for Matlab, this piece of code is just a symbolic expression that depends on 3 letters. We will apply chain rule, so multiplying the Jacobian of this thing and the Jacobian of y, which is actually this, because it's actually the derivative. Okay, so the product of the Jacobian of q and these kind of things will help me obtain the speeds of Q. Good. Let's check chain rule. First, the obvious way of doing this, if we know the trajectories beforehand. If we know the trajectories, I just substitute in here the actual expressions and I get a function of time. So, well, you know, the speed of components 1 and 2, it's just taking the time derivative. So I will store this as the speed of Q, and our objective is using chain rule to obtain exactly the same expression. That thing we called the speed of Q will be named as the so-called total derivative of this QYT that depends on 3 letters. It's just a normal derivative when everything is plugged in and it depends on only 1 letter, but so in order to name differently the partial derivatives of the function of 3 variables Q, YT, and the time derivative after substitution, so we call the partial derivatives when we have 3 letters in, and the resulting expression depending on only 1 letter, we will call it the total derivative. We will take Jacobian in this order, y1, y2, and t. So this is it. Partial derivatives of that expression depending on 3 variables will have 3 columns and 2 rows because it has 2 outputs. So theory tells us that multiplying the Jacobian by the time derivatives of the inputs, which is the second Jacobian, this kind, multiplied by the vector of time derivatives, because, okay, I don't put partial derivatives because there is only 1 argument, time. So this is chain rule, but okay, come on, the derivative of t with respect to t is just 1. So it is usually separated in formulas. It's just chain rule, but okay, that special thing, which is this, we call it the explicit term, in the sense that this 1 and minus 1 is just the normal contribution of the letter t in this expression. So we call that the explicit term, partial derivative of this thing with respect to letter t. And then this 2 by 2 matrix multiplied by this vector of 2 speeds is the fragment of chain rule in here. That's called the implicit contribution because y1 is actually a function of time and y2. Okay, so this thing is what's called the total derivative, but as in the first example with chain rule, our goal is obtaining the speed of Q, this kind of thing, but this only depends on time. So after multiplying the Jacobians, we need to do a symbolic substitution and replace y1 by its actual explicit expression of time and y2 as well. So once I replace y1 and y2 by the expression of time, then I have this kind of total derivative substitution made, and this is exactly equal to the speed of Q we're actually trying to reach. Indeed, if I tell the symbolic toolbox to compare those expressions for me, it tells me that the difference is 0. They are exactly the same. So we will conclude the video here. In this video, we have shown how to generate symbolic expressions from numerical functions. We have shown the use of the diff command and the Jacobian command. We have first shown that chain rule applies so that substitution first, i.e. composition, and then partial derivatives gives the same result as partial derivatives first, product of Jacobians, and then substitution. A second example showed the meaning of that chain rule when there is a special variable named time, so that the explicit time dependence and the implicit time dependence are handled with chain rule, and again the time derivative of the final expression is called the total derivative of this 3 input expression to differentiate that final objective from the partial derivatives and Jacobians arising from differentiation with respect to three inputs. Okay, this is it. Thanks for your attention. We finished this video now.